So the final talk is good classification of systems. So, floor is yours.
So my name is Lauri Himanen from Aalto University, PhD student. I'm going to talk about high-throughput structural systematic curation of data, systematic sharing of data, and intelligently reusing the data that we produce. And the whole goal of these methods is to go from trial and error based science to more data-driven discovery. And here are some like key ideas and concepts behind data-driven science. And some of the more concrete ones that are being used are, of course, machine learning, and there are big data frameworks, and as mentioned, we nowadays have quite a lot of these materials databases around. So let's just take a quick look at what I mean by materials databases. So we already got a nice introduction to OQMD and to other databases. And the basic idea is that we want to systematically store our computational results for later access and reuse. And there are multiple examples. There's Nomad, Archive, Afroleaf, Materials Project, OQMD. These kind of databases typically store, you have the geometries, properties related to the geometries, the methods used, and so on. But what typically is missing is material classifications. So let's just take a quick look at what I mean by material classifications. As I mentioned, what's currently quite often missing is the classification of entries in these databases. So for example, this is quite critical for the usability of the databases. So unless you're able to search for a certain kind of a material, it's quite hard to use databases in the beginning unless you crawl through all the entries. And it's really becoming the sort of automatic classification is becoming important to deal with large amounts of heterogeneous data. Now there are multiple types of material classifications. One can classify based on functional properties, so is an insulator, superconductor, so on. One can classify based on the material type, is it a polymer, ceramic, so on. Also there's the structural classification, which I'm going to focus on. So is this entry now a crystal structure, is the surface molecule, so on. Of course, if you have designed your own database from the beginning to only include crystals, then this kind of classification is kind of a trivial thing to do. But there are lots of heterogeneous databases which mix a lot of these different structural classes. And now I'm going to focus on structural classification in particular. So we started developing this kind of general concepts for how to approach structural classification. And our idea was to define a set of logical primary building units that you can combine to produce more complex structures. So basically, you have a set of primary building blocks, and then you combine these to produce more complex structures. Now these different combinations here can call, they form what you could call structural families. And instead of now visualizing this kind of a structural space in this kind of a data composition, it becomes more intuitive now to go to a tree-like representation. So now if we map these into a tree structure, we can arrive at something like this, what we call material structural genealogy. So it's a way of visualizing the structural space that's available. And the idea here is that we first start from the set of all materials, and then the first branch here is based on the dimensionality of the structures. So we have 0D, 1D, 2D, 3D structures, and then these branch out to more diverse, different sub-branches of structures. So this is just a way of like visualizing and categorizing the material structures we have. And now if we, with these concepts in mind, if we now come to the classification problem, so given an arbitrary atomistic geometry, how do we go on classifying it? So an ideal classifier would first of all detect these different logical components from the structure, and then it would also be able to, based on these components, map it into this structural genealogy, which is now understandable by humans and usable in these databases. So this is for the general introduction. I'm going to talk about our practical implementation of doing something like this for two-dimensional structures. So we're going to focus on this 2D branch of the materials genealogy. And in here we have 2D materials, surfaces, absorption systems, so on. And our particular classification goals are that we want to, we first have to detect the dimension in order to end up into this 2D branch. That's the first step. We want to distinguish between 2D materials and surfaces, so make this first branching in our classifier. But we also want to go a bit further, so we want to detect the unit cell of the underlying structure, so the unit cell of the surface or of the 2D material, and also distinguishing outliers. And by outliers I mean things like adsorbates, defects, and so on within these structures. So these are our classification goals, and I'm going to go a bit deeper into the actual algorithm that we use to do this. So these are the four main steps. First, the dimensionality detection, so determining is it a 2D structure or not. Then we go on to identifying the cell, which now quite accurately describes the underlying block structure. We go on to tracking, which I'll discuss a bit later, more in depth, and we also have the outlier detection to detect, for example, adsorbents. And now I'm going to discuss all of these four steps in a bit more detail. So we start with the dimensionality detection. So how do you, given an atomistic structure, how do you determine the dimensionality of this object? And what we use is the topological scaling algorithm. It's a bit slightly modified version of this. And the basic idea is just checking the scaling of the number of clusters when supercell sizes. So here we see for zero-dimensional systems, the original system is highlighted in blue, and we have made a 2 by 2 by 2 supercell. And now by simply analyzing how many clusters we end up with, we can identify the dimensionality. So for 0D, we start with one cluster, and after the expansion, we end up with 8 clusters. This determines that it's a 0D structure. And for the other end of the spectrum, we have 3D structures, where if you started with one cluster, do the supercell expansion, you end up once again with one cluster. And then there are 1D and 2D examples in between, where we have 4 clusters and 2 clusters. So this is a simple idea of determining the dimensionality of these systems, of these fully periodic systems. And next we go on to cell identification. So the problem now is we've detected, this is a surface, for example. We want to detect the underlying unit cell. So what we go on with is just a quite simple brute force search for these possible basis vectors. So we select a seed atom somewhere near the center of mass of the structure to start our search with. We just define a radius around this atom and select neighboring atoms which have the same element, define a set of vectors that build our initial guess for the initial set for these basis vectors for the unit cell. And these vectors are now then filtered based on certain criteria. So first of all, the periodicity that they now explain in this neighborhood. That's of course very important for the unit cell. We also filter them based on the orthogonality. So we don't want to select linearly dependent vectors. We want as orthogonal ones as we can find. And then of course also we look at the cell size, so in order to select sort of a minimal cell we can find. And now here we actually can do, by our definition, based on this cell that we find, we can distinguish between 2D materials and surface. So 2D materials will now have a cell that is repeated linearly only in two directions, and for surfaces we define that it must be repeated also in a third linearly independent direction. So when we find the cell, we also can classify if it's a 2D material or a surface. Now comes the tracking. So now, if we start with a structure shown here, and we have found the unit cell by looking at a certain local region within the structure, we now want to find, and based on this prototype unit cell, find all of the atoms that now belong to this structure, underlying structure. And we do this with a simple breadth first search. And here's a small animation of how it goes about. So what we found, the unit cell, we just go in a breadth first manner from the seed point to identify all of the repetitions of this unit cell. And the search dynamically responds to local distortions, so curvatures or sort of density variances in the structure. And the final step in the classification procedure is outlier detection. So it can be, often the interesting structures are not perfect, so they are perfect surfaces or perfect 2D materials. They have substitutions, absorbance, many kinds of things. And detecting these kind of what we say have named as outlier atoms, it can be easy if they have completed with different elements than the underlying unit cell or underlying material, or they are spatially very well separated. They are basically, the outliers are already then identified during the tracking procedure. But sometimes you end up with situations where you actually, for example, the adsorbates can have the exact same elements as found in the underlying surface, and they are in the exact symmetry locations where you would expect to find an atom in the surface. So then it becomes a lot more difficult to now identify that these are actually outliers. So in here we use a quite simple like a chemical environment check to distinguish is the part outlier or part of the surface. And now going on to a real application of this classifier. So we started out from the NOMAD archive. We selected roughly 400,000 geometries from there. Basically all the geometries we found for FHIMs and exciting. We run the dimensional detection to now be able to identify 15,000 different two-dimensional geometries. And now we run the full classification procedure for these 15,000 samples in order to do the classification. Is it a surface, a 2D material, and to identify the unit cell and the outliers. And now in order to now determine how good our classifier was, we actually need to do a visual inspection of the different systems. And we cannot go about visually inspecting these 15,000 candidates. So we narrowed these down to roughly 200 unique structures based on their chemical formula. And when now visually inspecting the results for these 200 different unique structures, we found that we got 99% accuracy for all of these three different properties. The classification in the surface or 2D material, identifying a correct unit cell, and identifying the correct outliers. So I'm just going to briefly show some interesting examples from this set of roughly 200 structures. So this is one which was dissected as a surface, and the image now shows the initial structure, and on the top right corner we have the identified unit cell. Then we have a 2D material which was detected, and now the difference here is that we have outlined the outlier atoms with a blue color. As you see here, there's a molecule on top of the graphene layer. Once again, we have the unit cell on the top right corner. We correctly identify a bit more complex surfaces which have different sort of coatings, terminations. Once again, finding the correct unit cell, identifying that there's two different terminations on the two sides of the surface. And we can also work with kinked or stepped surfaces. So this is an example where we have an uneven surface. We actually have what could be classified as a substitution, one atom substituted on the surface, and then an adsorbate molecule on top of the surface. So with this, I want to end with the conclusions. So with the advent of these data-driven materials science methods and materials exploration, we really need automated methods for classifying these structures, because simply visual inspection is no longer a valid option. We've introduced our sort of a general concept of how structures can be decomposed into structural units, and introduced the structural genealogy. And all of this, which I have discussed, of this classification algorithm, we have an implementation freely available. You can find the source code from this address. You can pip install it, try it out, and I welcome you to try it out and give any feedback for this. With this, I want to thank you.
Thank you very much. We'll see more and more examples of things being openly shared and being on GitHub or somewhere, and you can just download these things. It's really great thing. Is there questions?
Are you planning to implement it for 3D systems?
What do you mean by 3D? Like
Crystal structures?
So identifying crystal structures. Basically, because we already have this implementation for the dimensional detection, we can detect 3D systems, but now in order to distinguish between, say, a bulk water and a crystal, this becomes a bit more complex issue. So I have some ideas. You could take a look at the symmetries in order to distinguish maybe between amorphous kind of things and things. But the implementation is not yet here. But it's a good idea, and I think it can be done.
Out of the 192 structures you tested, what were the one or two misclassifications?
Okay, here. So we have two systems, and they're quite interesting. So we for both of them we were able to identify them as surfaces, but what we miss here is either the unit cell or so for example, this is one of the examples where we actually have not identified the correct unit cell, and the reason here is that we didn't identify correctly these outlier atoms on top of the surface, but this atom here is identified as an outlier. And what I think is going on here is that because this atom is actually missing from here, so the algorithm cannot decide if this is an outlier atom or if the structure is missing an atom here. So this is actually quite of a tricky case for the unit cell detection, because we basically don't have enough statistics in the original structure. And the other case of these two from from Aalto 200, we have not correctly identified this carbon atom as an outlier. And the reason here is that it's so tightly integrated into the surface in the exact symmetry position where you would expect in this material.